Imagine two Earthlings, Tom and Stella. Now let's zoom out and pretend that Earth is near a black hole. Stella blasts away from Earth using her jetpack, and she comes to rest at a coordinate r equals 10 gm from the center of the black hole, where m is the mass of the black hole, and g is Newton's constant. Out of fuel, she begins to fall towards the black hole's center. How long does it take for Stella to fall, according to her watch, and also according to Tom's watch, back on Earth? Let's find out. A black hole curves space-time according to the Schwarzschild metric, as discovered by Carl Schwarzschild in 1915. We will cover this discovery in a future video, but for now, let us use the Schwarzschild metric as a description of the space-time surrounding a black hole. The Schwarzschild metric equation uses a coordinate system where t represents the infinitely far-away time of an inertial observer who is stationary with respect to the black hole. We will assume Tom satisfies these criteria, namely that he is sufficiently far away that his space-time is relatively flat, and we will ignore the small effect of the Earth's gravity. The ds squared on the other side of the metric is the invariant quantity that Tom is measuring, which in this case is the negative of Stella's proper time squared, a fact we encountered in a previous video called the machinery of general relativity at the 1-minute timestamp. So let's put a clock by Stella, who measures her proper time, tau, and also a clock by Tom, who measures faraway time, t. Now in the case of radial infall, there is no motion in the theta or phi directions, so we can completely ignore the azimuthal terms in the metric equation. Now let's analyze Stella's infall with the help of the geodesic equation, developed in a previous video. The geodesic equation is actually 4 equations because alpha ranges over all 4 coordinates, including the time coordinate. The only equation we will need to analyze Stella's motion is the one where alpha is set to the time coordinate. So let's set alpha to the time coordinate in the geodesic equation. In order to use the geodesic equation, we must identify the metric tensor components. GTT is the coefficient in front of the dt squared, and GRR is the coefficient in front of the dr squared. See video 9 for an example of this fact using polar coordinates in flat space. The first term of the geodesic equation has the index beta sum over all 4 coordinates, so let's write them out fully to understand what is happening. The only non-zero component in this sum is GTT, since GTR, GT theta, and GT phi do not appear in the metric equation. So let's get rid of the components which are 0, and then substitute the value of GTT into the geodesic equation, which is negative 1 minus 2gm over r. Also note that none of the metric components have an explicit time dependence, so the last 16 terms in the geodesic equation vanish as well. Since the derivative of the term inside the square brackets is 0, it follows that the term itself is a constant of the motion. But what is this constant? To answer that question, we can look back to the metric equation. Let's divide the metric equation by d tau squared. And now let's use our initial condition that when r equals r naught, dr d tau equals 0, because that is when Stella began her fall from an initial velocity of 0 at the location r equals r naught. So let's make that substitution into the Schwarzschild metric equation. Now let's rearrange the equation and take the square root. This is the value of dt by d tau evaluated at r equals r naught. Now let's multiply both sides of this equation by negative 1 minus 2gm over r naught. The left-hand side reduces to negative the square root of 1 minus 2gm over r naught. The right-hand side of this equation is a constant of the motion, as described by the equation below. So if negative 1 minus 2gm over r dt by d tau equals negative the square root of 1 minus 2gm over r naught, when Stella is at r equals r naught, it remains equal to this value for all r that Stella falls through. Therefore, the constant in the equation below is negative the square root of 1 minus 2gm over r naught. So let's make that substitution. Now that we discovered the constant of the motion, let's go back to the form of the Schwarzschild metric, when we had cancelled out the d theta and d phi terms, but we are not evaluating at r equals r naught. Once again, we divide by d tau squared. And now let's solve for dt by d tau in our geodesic equation and substitute that into the Schwarzschild metric. Let's simplify this equation by multiplying both sides by 1 minus 2gm over r. And finally, let's rearrange to solve for d tau. There, that's good enough. Now let's make the substitution that r equals r naught sine squared theta, because this will help us solve the integral. This substitution makes sense because then r can have a maximum value of r naught, which was Stella's maximum value of r, and a minimum value of 0, which is Stella's minimum r value. Of course, this is because sine squared theta varies between 1 and 0. Now let's factor out an r naught from the denominator to discover it cancels with the r naught in the numerator. And we use the trig identity that 1 minus sine squared theta is just cos squared theta. And now we take the square root of both sides of the equation. Now let's take the derivative of r equals r naught sine squared theta in order to find out what dr is and make that substitution. The cos thetas cancel, and we substitute the elementary trig identity that sine squared theta equals 1/2 of 1 minus cos 2 theta. The 2 cancels with the 1/2, and now it's time to perform the integral. Let's switch the limits of integration on the right-hand side, which will cancel with the negative sign on the left-hand side. Now the integral on the left is just tau, whereas the integral on the right is theta minus 1/2 sine 2 theta. Before evaluating, let's write sine 2 theta as 2 sine theta cos theta, and then write cos theta as the square root of 1 minus sine squared theta. The 2's cancel, and now we must write sine theta in terms of r using the equation below. And now it's time to make the substitution for theta. And now we must evaluate the expression between r naught and r. Now the inverse sine of 1 is pi by 2, and the second term cancels because of the 1 minus 1. So we can go ahead and simplify this expression further. Now let's finish up by solving for tau. Now that we have an expression for proper infall time, let's put in the value of r naught equals 10 gm and r equals 0 to see how long it takes Stella to fall to the center of the black hole according to her watch. The term out front is root 500 gm. The first term inside the brackets is pi by 2, the last term inside the brackets is 0, and the middle term inside the brackets is multi-valued. It equals 0 plus pi times an integer. Let's say the black hole that Stella is falling into has a mass of 20 million solar masses. Plugging in this value to the equation, and using g equals 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, yields a value for tau of about 9.4 times 10 to the 28 Newton meter squared per kilogram, or 9.4 times 10 to the 28 meters cubed per second squared, since a Newton is a kilogram meter per second squared. This can be converted to seconds by dividing by the speed of light cubed. This yields a result of about 3,500 seconds, or approximately 1 hour. Notice, however, that our result is multivalued, with the answer of 1 hour corresponding to the n equals 0 case. N equals 1 corresponds to 3 hours, n equals 2 corresponds to 5 hours, and so on. What do these other proper time values mean? One interesting interpretation is that they correspond to stella oscillating in and out of the black hole, just as is the usual kind of prediction made by the Newtonian case. So the black hole spits back out stella every 2 hours or so, according to Stella's watch. But what about Tom? We will discover what happens according to Tom in our next video. Thank you for watching.